Today I'm going to talk about two different topics. First, I'm going to talk about 3D scene reconstruction from a single image. And afterwards, I'm going to talk about BlenderProc. BlenderProc is a procedural pipeline to generate data for the training of neural networks. So this first work was joint work with Rudolf Triebel. He's my PhD supervisor. And before I dive in, I'm going to talk a bit about myself so you have an overview of who I am. I joined the DLR in 2013. The DLR is the German Aerospace Center where I work. It's all over Germany. We have many locations. I personally work in the Institute of Robotics and Mechatronics, and more specific in the Department of Perception and Cognition. And Rudolf Triebel, the co-author of this work, is my PhD supervisor and also the head of the department I'm in. Since 2017, I'm a PhD student, and I mostly work on robotic-related computer vision tasks. And I've spent a lot of time in my last years working on Justin. This is the humanoid robot here on the left you can see, which we use in a variety of different scenarios. I'm going to use it through the lecture many times to refer why we are actually doing some certain things a certain way. So let's dive into the paper. Here, the whole goal of this approach was, how do we get from one single color image to a complete scene? Not just depth, not just monodepth estimation, where you only have one pixel, one depth information per pixel. We wanted to construct more than that. So if you watch this, you can see here that in this color image here on the left, which we have as an input, we can predict here in our prediction, even stuff which is hidden from the current camera view. And that was the whole goal of this approach. How do we reconstruct a complete scene, including hidden and occluded areas? And you can imagine, of course, this is not such an easy task, because seeing around the corner isn't something anything is good at, being it computers or humans. We furthermore, of course, use here color normal image, mostly because normal images have the nice property to guide our approach locally, because they offer local information about the neighborhood, and this can be used to improve the results. How we obtain this, I'm going to talk about later on a bit. So if we watch this, we can see how the scene gets kind of well reconstructed. Before I talk about how we did this actually, let's motivate that a bit. Why do I do this? Why is this necessary? So imagine we have a robot like Justin here, and we are in this kitchen, and Justin now sees this view from its cameras in the head. And now what we want to do is we want to plan a route through this room, and for that we need a reconstruction. We need the current scene so we can plan to navigate in here. And then we get something like this. By the way, if you're interested, all of these videos were generated with BlenderProc, the topic of my second talk today. So if you want to use that, feel free. Most important here, there's many different 3D representations I could have used for this approach. I will discuss a few of them before we dive in what I did. A lot of people in the past have used voxels. Voxel representation is quite simple in its way that it is free or occupied. Then you have this binary classification for your space, and each voxel is either free or occupied. As you can already imagine, this gets really computational intensive if you have a high resolution. So this is usually used in low resolution shapes, mostly in reconstructing simple shapes like planes, chairs, or such things. Then there are other approaches like meshes, point clouds, or techniques, I should say, which use these. Great advantage there is that you need much less memory. The biggest problem is, how do you map them from the image domain to these meshes or point clouds? In recent works, a lot of people have used a Latin encoding for that, so that you start from an image, then you go down to a Latin encoding, maybe 256 of size, and then you go up to your mesh or point cloud representation. And that kind of works well for shapes, for single objects in space. However, to be honest, I found not that many applications in the real world where you have a plane on a white background and then you ask yourself, oh, now I need a 3D representation of this model. And as I have my doubts of the application of these specific methods in the real world, scientifically, they're of course extremely valuable and interesting, but the application, which for us computer vision guys who work on robots is always really important, is a bit doubtful here. Most important here is, of course, that this does not generalize to scenes. So you started with a single shape, but you cannot easily extend it to a scene because scenes are open. There is no closed boundary on all sides. And then you have this problem, how do I address this properly? Of course, there are other approaches like octrees. Octrees are a bit like voxels in the sense that you also divide your space along the axis. However, you only split here if there's actual content inside of the octree you're currently looking at. Biggest problem here is again that you have this decision during the training and prediction step on the GPU. First of all, GPUs are not that great in dynamic routing. And second of all, the training is quite tricky. For example, if the training fails at recognizing that a certain split is necessary, you won't get any more information there, which is tricky while training. And then there are a lot of different approaches, which I'm not going to cover too much in detail. We have descriptors and multi-view and RGBD, so more image-based approaches where you save the image and then try to reconstruct based on this one image or several images on the scene. Then we have graphs, which are a bit similar to meshes in a sense, projections, and lastly, cut models. In cut models, in contrast to meshes, you can define curved surfaces as you're not limited by vertices or triangles, which might be useful in some applications. But again, for most of them, it's hard to link a certain pixel in the image space to an output, whatever it be in the output space, if it be a point or a voxel. And for sufficient training, we found this linking is really important. For that reason, we use a projection. So as I said before, we start with this single RGB image and want to reconstruct the full visible scene. As you can already tell by this one image here on the right, that we have a near and far plane. So if you've ever dealt with a camera system before, this is what you see here, then you know to have such a projection matrix, you need a near plane. So everything before the near plane gets clipped. In this instance, we used a meter. So everything closer to a meter is just discarded. And then our far plane in this instance is 4 meters. As we usually use this in indoor scenes, 4 meters is a good compromise between having enough to see, but not too much or getting that stuff too cramped up. And now we use this camera system and project it inside of a cube. By the way, Peter has already said it, but if you have any questions during the talk, just interrupt me completely rudely and ask me directly. It's the main reason we're all here today, that else you could just watch the video in the end. So please feel free to ask anything. So after we've done this projection step and we are in this cube, we can then voxelize it. And we use here a resolution of 512 to the power of 3. This is a lot. 512 to the power of 3 is roughly 134 million values per scene. For comparison, if you have an image with a resolution of 640 by 480, which is already a lot for deep learning related tasks, then you have 300,000 pixels. Compare that to 134 million values. So getting that on a GPU and getting it trained is tricky or impossible, at least at the current stage with our hardware. Maybe in the future we're going to get GPUs with a terabyte of VRAM, but for now we have to dream about such things. So we have this high resolution we aim for, so we need to find a solution for that, but I'm going to cover that a bit later on. First, let's talk about a TSDF volume. So what is a TSDF volume? TSDF volume is a bit of a combination of of the voxel space I discussed earlier, and of a subpixel accuracy mesh. How does this work? So we voxelize here our space. We do this in 2D because it's easier to visualize. And here we save in each voxel the distance to the closest surface. So we look at each voxel center and then we blow up a bubble and wait until the bubble hits something. And if it does, we save the radii of this bubble, of the sphere. And this is then the distance for this particular voxel. We repeat this process for all voxel centers. And for voxel centers inside of a TSDF volume, we use negative values. So we have positive outside in the free space. And if we know it's filled, we use a negative value. And we repeat this process for all voxels. And then we end up with something like this. And this is called truncated sign distance field. Truncated because we truncate the value at a certain point, here at 2.5. So because at a certain range, it doesn't really matter anymore in which direction the closest surface is. Imagine being in the middle of a big room. It doesn't really matter where the next surface is. It's only interesting now that we know, oh, there is no surface around. Of course, you can define this truncated value as you need, depending on your application. Then there's the sign value, which I already explained, that you know what is free and what is occupied. And then the distance value, name in this word. By the way, I'm just going to ask now several times if you have questions, else I feel like no one is interrupting me. Do you have questions so far? Did I anything?
Yeah, I might have missed this if you mentioned it, but how do you deal with scenes that have different depths? So here you were showing a kitchen, but what happens if you're looking at a living room, which has like in real life 3 times the volume?
So we're always looking just at a camera system. So if you have your camera view of your scene, then it already clips right and left, because predicting outside of that is even harder. There are works which try to do that, but it's really, really tricky. And for the depth, so if our scene is deeper than 4 meters, we just clip off and we say everything beyond 4 meters is not of interest right now. As I'm working on a robotic system, in this instance, I could just drive there, or if I could get any closer and look up what is there.
Okay, so you clip a boundary box to make sure that everything has sort of a homogeneous volume.
Yes. Any other question? No? Okay. So I already mentioned getting this giant TSDF volume on the GPU is impossible. It's just too big to actually train it then. So what we need is we need to compress this giant space down. So what we do is we look at these blocks and try to compress it down. So we pick one of these blocks. First we split them up, of course, and then we use one of those blocks and compress it down with an autoencoder. So we trained a simple autoencoder on these simple blocks. Each block here has a resolution of 16 to the power 3, so not that big. And we compress them down to 64 values. If we train this on a sufficient big data set, we usually get a really well and stable encoding here, where we can represent free or filled spaces or anything in between. And this compression then makes it possible to train it on a GPU, because then our space is not 512 to the power 3, it is only 32 to the power 3 times 64. And that we can more easily manage. So let's talk about now, how do I get from a 2D image to a 3D scene? Because there's this transformation step where you just have a plane and then you have something in a volumetric space. How do I get from an image to a 3D space? And for that, we designed something we called tree-net architecture. And to understand it, we got inspired by AlexNet or ResNet, where you have more than one path in your network. And here we split our complete frustum here, our complete cube, depth-wise and say the front part is predicted by one path and the back path is predicted by another path. And these paths together then have both information contained. So what I imagine, both of these paths, of course, contain convolutions and so on, and some rest node blocks. But both of these paths then have to learn how certain objects look at a certain distance. So I imagine that the block in the front learns that objects which are big, like imagine you're having a bottle, which is usually kind of fairly equally sized depending on the distance. And then you can determine how close it is to the camera. And then you try to create a positive feedback here in your network. So
just use a depth camera.
Sorry, didn't get that. Could you repeat that?
Why not just use a depth camera if you have a robot?
So, of course, you could use a depth camera. Problem with depth cameras are numerous. First of all, depth cameras are sometimes inaccurate, especially on shiny surfaces, or have other, depending on the depth sensor. Of course, you could use TOF at time of flight, which sends out a signal and then waits for the signal to come back. Depending on the surface, this might not lead anything back if the surface is quite dark, or it is shiny and you don't get any useful information back. So there are always difficulties with depth cameras. Of course, this could here help. The problem is it's not really easy to incorporate into this idea we had for this approach, where we wanted to reconstruct a scene completely. And if you already fuse this 3D information into a 3D scene, so you could convert your depth image, which you could get from a stereo sensor or whatever sensor you use, into a point cloud, and then try to fill in the voids. What we discovered is that sometimes this doesn't work really well, especially to fill in gaps, because it's unsure about the direction of the camera in the scene, because you lost that information while transferring it to a point cloud, which is usually really important.
Actually, it's a good time to ask, is there research that you did or somebody else did about this combination of 3D reconstruction with RGB and then adding in a depth aspect, and what were the results?
So I'm going to cover this a bit later on, but let's do it now. The biggest problem here is that there is nearly no research in that area. I'm one of the first persons who tried to do complete scene reconstruction based on color images. And what a lot of people do is shape reconstruction of singular objects. But as I highlighted before, I personally find it less useful because you usually don't have that case that you only have an object on a white background. So sadly, the reason I believe why there's so less research in that field is because of the missing data set.
Yeah.
There's no good data set where you can just test a new approach on. We have ShapeNet for objects, but there is no data set for scenes, which is a bit sad in that regard.
That's what BlenderProc is good for, exactly for these things, maybe.
BlenderProc is more image-based than 3D space, but in that project here, in this first project I'm presenting today, we wrote a piece of software, which I'm going to cover a bit later on, where it is about getting the data for this, because we needed to find each TSDF value for these scenes. You couldn't just download a data set for that because there is no such data set.
Also, I'm sorry that it's a bit moving to the depth again, but that's an interesting point. What did you try? What type of merging did you try that you saw that has potential to work between RGB and depth information?
So do we have a depth sensor, or did we predict the depth with a mono depth estimation approach?
You have a depth sensor and you have an RGB image of the scene. Okay. And you want to 3D reconstruct the scene. Which approach would you say is optimal or better?
If we already have a depth sensor, assuming we do, which we didn't assume in this work, if we already assume we have one, then it might be better to represent this already in a 3D representation, because most depth sensors, especially if you get a new one, have a really well, how do you say that? Have a high accuracy.
Yeah.
And then you are in 3D already, and then you could try to only fill these approaches. There's really interesting work by Angela Dye in that regard, where they tried to fill in these voids.
Yeah, they used encoding, I think. They took encoding of the image and then some encoding of the 3D space and merged them, if I remember correct.
Yes, this is one.
That's what you mean?
This would one possible way, but there are different ones. She has, I think, at least 4 papers on this topic where she tries different approaches, where one already has kind of nearly filled in mesh, and she tries to fill in the gaps, which happens a lot if you scan in rooms. Of course, the scan in rooms always takes a lot of time. It's not something you can do easily. And what we wanted to do here is find an approach which can do this easy and quick without having to scan in the room. Imagine you have a robot system which gets into in a new environment, like a burning house or something, and it has to create a map quickly. You don't have time to walk around, oh, what is behind this chair and what's behind that table? Can I navigate there? We humans would automatically see that. We see an indoor space and we could immediately tell, oh, there's probably free space here. And that is the goal here. We're trying to, with as little knowledge as possible in the beginning, to get as far as possible in the end. Mm-hmm. Because if this is possible, we can probably do more afterwards. Making the challenge as hard as possible to show this is possible, then the rest should be easy.
Mm-hmm. Max, after the talk, I will ask you to just give me the reference to the Angela Day research that you know that touches these things, so we could send.
I will add them. They're not in this presentation right now, but I can add them later on.
I think also somebody raised the hand, but I don't know if this means that you want to ask a question or is it by mistake?
Oh yeah, I actually had one question for Maximilian. This is Neeraj here. My question might sound a bit basic, but you just talked about TSDF. Mm-hmm. And I have heard about TSDF being used for back projection, specifically in some papers. So is TSDF used for back projection, or is it used complementary with something else, maybe a neural network for back projection from a 2D image to a 3D space?
To clarify, TSDF is just, as far as I understood it, the process of saving a space with the distances to the surfaces, which you could then reconstruct again to a mesh with a marching cubes algorithm or something like that. Are we talking about the same thing here? Because based on that, I didn't fully understand your question then, because you could, of course, use this as an output and then try to use this as a reconstruction target. If you have what a lot of people do, for example, if you want to reconstruct a scene based on moving 3D sensor, they usually use projected TSDF volumes where you insert your camera into the scene, and along the camera array, you save the distance to a certain object. This is not like here because we do this omnidirectional in all directions. We save the distance. This one is only done in camera direction.
Okay? Correct. So that means that we already have the depth information with us, right? For us to know where along the line, where along the ray, the object lies. So for that, we need some prior depth information at hand, either through a depth sensor or basically through a depth sensor, right?
Yes, so if you want to reconstruct or construct such a TSDF volume in a real scene, you need some kind of depth sensor or a color sensor where you use a mono depth estimation approach.
Exactly. So my question was where if depth sensor is negated from the equation and we want to project a 2D image into a 3D space,
yes,
then where does TSDF come into picture? Like, what point?
So we have in the beginning our color image, and we have in the end as output our TSDF volume. So the TSDF volume is the target here, in this regard not completely because we use the TSDF compression to compress it down, but we try to get from the image to the final TSDF volume, being it in a compressed form. Okay? And for that, I developed this tree-net architecture. Maybe I'm explaining this slide here, and then maybe it gets a bit more clear. Okay? Should we try that?
Awesome.
Okay. So
another question. The depth estimation is from one camera or from 2 cameras? Because I see that Justin have 2 cameras in his eyes.
He has two, but those are not the cameras we're actually using. We're using a real sense, which is on the head, because these two are only used for teleoperation. So teleoperation is the task where other human controls a robot. They're extremely tuned for this task and are not well fit for other computer vision related tasks. So there would be, of course, we can always use a depth sensor, but assuming now for this work, we don't have a depth sensor, just for the sake of argument and to show what it is actually like if you don't have depth information, because a lot of robotic systems don't have depth, especially if you have small robotic systems or drones, where this added weight of a sensor which carries also depth would be too much.
So the depth estimation is from a single RGB photo.
So for now, we only have one color image, RGB, no D, no depth. Okay, perfect. So coming back to this, we now have our TSDF volume projected into this cube, right? And what we now do is we split this cube in half along the depth. So we split it, and the left side is now predicted by one convolutional path, which only takes care of this back part. Then we do this again. And we again have two paths, one for the back part and one for this back front part. And we do this again. And as we're always binary splitting, we get a tree architecture. We get this convolutional paths, which are responsible for reconstructing these depth slices. It's a bit weird to wrap your head around, but try to imagine that each of these paths is responsible always for the back and the front part. And you repeat this process until you get these depth slices. And then what you do with these depth slices, you combine them back together. So we have now here our tree on the right. As you can see, this left part is now used as the front slice. Of course, it's not really these values which we predict here. This is a deep learning approach. So we have some feature space, we have some feature representation in these values, but we now concatenate these feature representations in the beginning and treat them as the front or the back part. Okay, and what we can do then is we can get from a 2D image space to a 3D space, because this transformation is not simple. If you just did this in one step, so we could have used theoretically, and we tried that in tests first before we came up with this. You have your convolutions and you have your feature channel. You could just use your feature channel as a depth channel, right? But then the network has to do this one step from 2D to 3D in one single operation. And that didn't work in our tests. We assume that this transformation from 2D to 3D is so complex that it needs a couple of convolutions to actually make it work. And with that, we found a way of doing this nicely in a condensed way. Problem with this here is now that you create a bottleneck, because you only create one 3D block. These 3D blocks here have a resolution of 32 to the power of 3, and our output, as I mentioned earlier, has a size of 32 to the power of 3 times 64. So better would it be if we already have a higher resolution, a higher amount of 3D blocks here. For that, we use something we name multipath. And so we have here on the top now our leaf nodes. And these leaf nodes now just have more channels. And each channel now is used, each channel block is now used in a different 3D volume. So you use the front part for the first 3D volume, the back part for a second. If you have more, you can of course split that more as you need it. And in this instance, then we can get up to 64 of these blocks. So we first split, and then we have here on the left side 64 times the features for the front part of this 3D scene. Is that clear?
I'm not sure I understood exactly. Could you repeat?
Which part? The tree part or this multipath?
This multipath.
Okay, so we now, maybe going back here, we now had here concatenated all these feature channels to construct our 3D volume.
Okay.
And this 3D volume now would be a bottleneck because we only have one of these 3D volumes. If it's only 32 to the power 3, it's not that big. And while training, we realized, oh, this is not enough. So what we did is we use several of these 3D volumes as an output. What happens now, here in at the top, we have our leaf nodes. And each leaf node is now divided. So we have the first part of the feature channels is used for the first 3D block. And the second part is used for a second block. But both of them are used in the front, so that the outermost left leaf node here is still responsible for predicting the front of our 3D scene. And the block completely on the right is then responsible for predicting the last block in our depth frustum. So if this is the depth, then this last slice here is predicted by this node here on the outermost right.
So you have like 16 targets, which you can concatenate afterwards. So you're doing backprop on 16 different channels on every iteration there?
Yeah, of course, the information then flows back through these blocks, then divides up on the different nodes, and then flows up the tree.
Do they have common layers at the start? Or
so we start with images with a resolution of 512 to the power of 2, and then we go down to 32 with some convolutions and max pooling, and then we have this 32 condensed feature channel, which we then split over this tree architecture.
Thanks.
And then
when you're saying 32, you mean multi-paths 32 or 32 layers
no,
for each path?
Spatial resolution of 32 to the power of 2.
Okay.
The tree usually has, we have tested different heights to see if that has a strong effect. We just learned we need one, but the differences between, we're going to see that later on in the quantitative results, between a lower height and a deeper height is not that big.
Okay. I might ask later to come back to this, just maybe I need to see more to understand fully.
Okay. Good. What was I? So after we talked about how do we get to this, we learned during training that it is really crucial to have some kind of focus, because we use this giant space and a lot of, which is a bad habit of all voxel representations, that a lot of it is free. And predicting free space is not that important, especially if you use a Latin encoding. So we had these 16 by 16 blocks, which we compressed down to a Latin encoding. And now we try to reconstruct this Latin encoding perfectly. And if we now have on the Latin encoding for free space, an error of, let be it 0.1, and we have on the surface an error of 0.1, both of them would be weighed equally, even though changing the free space wouldn't be that beneficial anymore. For that, we need something we named loss shaping, where we try to focus the attention of the network on the boundaries of the approach. So here we start again with some blue object, and our camera is placed on the left, because now it's really important where the camera is and what we see. And we increase the weights around, sorry, that didn't work. We increase the weight around the boundary. So to say that if it's close to the boundary, we multiply the loss by a weight of 100 here. For free space, we do that too. We use a weight of 2. If you ask me now if I would choose these values again, I would say no, but we picked them in the beginning and recreating them takes around a month, so we didn't do that because time frame and computational resources, I guess, are always limited, not just for us, hopefully.
What would you choose differently?
Let me finish this explanation and I tell what I change. So we have here for the back, for surfaces which are visible from the current camera view, like this one here in the back, we used a value of 0.15, which is probably too low. And for the space inside, which is usually quite unimportant, the difference between filled and not completely filled is not that important at the end, because we're not so much interested in that. We're more interested, where's the boundary? Where do I need to be careful to not collide with something, and it's not super interesting. Oh, this block deep down in this wall is actually filled. And then for the free space behind objects, we use kind of a flat filling, which if it gets further away from the visible space, from the free visible space, the weights go down. Why is that? We argue here that it is harder to predict a hole or something, how do you say this? An obstacle behind something if you can't tell where the free space is. And if you go further away, we increase the weight to not throw off the attention here. So as I said just now, and Peter already asked, why would I change these values now? So as you see, there's a big discrepancy between the boundary, this first boundary, which was at the time really important to us, and also the free space. And we didn't focus too much on this space behind it. Now I would shift this focus a bit. I would decrease this 100 probably to 2, the visible space here 2, maybe to a 1, and then increase here for the back. Of course, I would keep this low weight for the inner space because it's still unimportant. And usually if it's wrong, it doesn't matter that much, because imagine you're having a house, and behind your wall, the network predicts that there is an object, which is usually not that important anyway, because you can't reach through the wall anyway. So it's not really important if it messes up in that regard. So this low value would be here completely fine. So you see, we would shift a bit the focus here, maybe for the next work. So after we've done this loss shaping on the output, which greatly improves the results, you will see this later on in the qualitative evaluation, we did a further thing. We used a loss shaping directly in the tree. So here on the right, I visualized our tree I discussed earlier, and each of these splits is again this back and front split. So we have here in the second level here, this orange block, which corresponds in our 3D space to this yellow slice. What we do now is we take the corresponding yellow slice of the compressed encoded TSDF volume, which had a resolution of 32 to the power of 3 times 64 for the Latin encoding, and take it out, the slice, and then we average in the depth. Why do we do that? Because at this state in the tree, we do not care about the fine details in the depth. We only care about the overall structure in this certain depth slice. So we average in the depth, and then we compare it to the current node. For that, we use a 1-by-1 convolution to just change the filter amount to get it correctly. Then we compare them and use the loss block, the loss shaping we used on the last, introduced on the last slide, and calculate the loss. This does not change the performance much, to be honest. It gave us 2 to 3% on the performance, but what it does, it changes the training time drastically. Instead of training for 2 to 3 weeks, we can now train in a matter of days. Now maybe 4 to 5 days, which is a lot faster if you want to test out certain things. So this was one of the great steps which made it so much easier to test, because it, during the training, focuses the attention of the network on these depth slices. Make sure that the tree already knows, oh, this particular node in my tree needs to represent this certain depth slice. This helped a lot. Okay, so any questions so far? I hadn't asked that question for a while, sorry.
I have, but if anybody has before, go ahead. No.
It might be redundant and coming back to the start, but why did you choose the TSDF volume over a mesh representation at the start?
No problem. So the problem with a mesh is that you have a hard time linking individual pixels to the output. So imagine you're having, I don't know, a pixel on a couch. How do you link this one pixel to this vertices or this in the middle piece on a triangle together? And here, through this linking of the pixels directly to the position in the output space, we get a nicer flow of information.
Okay, so this matters a lot because you're trying to use this to navigate the robot, but if you were doing something like 3D art generation, it would matter less as a problem.
It would always matter if you reconstruct a scene.
Okay.
If you only reconstruct shapes, like a closed off shape, being it a plane, a chair, then it doesn't matter that much because there's already a lot of work in that regard where they have shown that you can encode a complete color image inside of a latent representation and then go back up to a mesh.
Okay.
But for a scene, I mentioned earlier that it is too complex. Scenes are just, there's such a variety of possibilities. You can't have this closed assumption, and then it gets really, really tricky.
Okay,
I tried that in the beginning, but that completely failed. Maybe someone else will find a solution to this because I believe meshes would be such a nicer representation because they're so much more condensed. But sadly, we cannot map the image plane back to these meshes easily.
Okay. Thanks a lot.
You're welcome.
I have a question a bit about definitions. You started to talk about it, but I think maybe I missed something in the understanding. A slice, so you have a box here on the left, which is 32 in the power of 3, which is just a small part of the whole scene, which I think you said is 512 by the power of 3, right?
Yeah, but we used the compression to get to this. So our initial had 512, then we compressed blocks with a resolution of 16 to the power 3 down to one value with 64. And then we get to this 32 to the power 3.
Ah, okay. So that was
This
also
this is the complete output in the end. This entails everything. You just need a decoder again to recreate your scene. So we predict this imagine now we have one run through. We have our color image. Maybe we have our synthetic normal image. Cover later on that. And predict then with that this encoded output, and from that we use our decoder to decode each block, and then we get again our full scene. Then we can use our marching cubes to generate our mesh if that's necessary. In robotics it's usually not, because we can directly plan in a TSDF volume, because we know for each block, oh, the boundary is 2.5 meters or something like that away. So it's quite easy then to plan.
So the 32 to the power of 3, that's actually, let's say, an encoding of the entire scene.
Yes.
So that's okay. And then we have the different slices. And for each slice, we have a different leaf in our tree that is encoding the representation of that slice, right? Okay.
Correct.
And now I want to go back to the multipath. You mentioned that when you didn't use multipath, just one path, there was an issue, and you saw that multipath solves it. Could you explain maybe again what was the issue and how the multipath works?
So if we saw here that our output has 32 to the power 3 times 64. So we're here in a 3-dimensional space with 64 feature channels.
Yeah.
2D, they're stacked after each other. In 3D, we can stack them next to each other.
Okay.
So we have 64 different blocks.
Yeah.
If we now use here only one block, we create a bottleneck, because we then only have one block with 32 to the power 3. And then we would go back to the 64, and that didn't work that well. It worked, but not that well, because it was able to get rough shapes, but not really precise.
You needed different encodings for each one of the 64 features per block or per.
Yeah, exactly. This 16 to the power 3 voxel, which we encoded in 64 latent values, would now be too hard to get in one value. Is a bottleneck in between here.
Okay. Okay. Thank you.
You're welcome. Okay, because of time reasons, I'm going to go a bit quicker now, because we started a bit later than I expected. But let's talk about data generation. So as I mentioned earlier, there is no data here. No one ever did that before, because people are only focused on single shapes so far. Maybe this will change in the close future. So what we had to generate was first enough data points to train our approach. We generated around 130,000 data points. That entails, for each data point, we have a color image, which you see here on the top, which was generated by BlenderProc, software I'm going to cover on later on. Then we had a synthetic normal image, also generated by BlenderProc. Then we had our TSDF volume. For that, we had to write some piece of code which can generate for 134 million values, these voxels in our space, the distance to the closest polygon. So we developed some algorithms to do this quite quickly. It's a combination of octree, fast lookup, and flat fill to get these values quite quickly. So we now need around a minute per scene to calculate these SDF values at such a high resolution. And what we then needed, we needed to train an autoencoder to get down to this encoded volume, the 32 to the power of 3 times 64. And we had to calculate the loss map. The loss map was also calculated on the high resolution scene. And then we averaged it down so that we get, even for small details, which might be lost in an averaging process before, an accurate loss value. Compressed, this all is around a terabyte of data, compressed. And this is high compression. So first we used on the TSDF volume a quantization to save this in 16-bit ins. And then we compressed everything with a strong compression to even get it closer, because also I couldn't have stored this on any disk. Just for comparison reasons, ImageNet has around 150 gigabytes. And this is massively bigger than ImageNet. And just because of these giant TSDF volumes, the output space is just giant. Uncompressed, I think one scene has around 520 megabytes for one 3D scene, which is a lot. So we have this giant representation and we needed to find a way to calculate them quickly and finally encode them. If you want to know more how we did this encoding and calculating of the TSDF volume, I highly recommend the paper in that regard because it's too detailed for this presentation. So after talking about the data generation, let's look at some results, because we talked so much about how this actually works. How does this compare? So now we have here our normals, our normal images, still synthetic, and the image in the middle, we always have our ground truth. And on the right, we have our prediction. One thing which I should say for this prediction, which I probably should have said a bit earlier, is that these purple areas here are regions where we don't have any color information. As we only have this one color image, we cannot estimate a color for regions which are not visible right now. So we usually just make them purple to make them a bit more distinct. Okay. So as you can see here, we have this couch now and up above this kitchen scene, and both of them are constructed quite well. We'll get your overall shape of the couch here without any problems. You can see the wall here. There are some artifacts here in the back. These are because of the loss shaping we did. We reduced the loss in these regions so much that sometimes the network is predicting some weird artifacts here. To be honest, that is not such a major concern. It's for the visualization a bit bad because it looks not so nice, but in a real application, you're not that interested what is behind the wall. That is not usually something you're interested in, so it's not too bad that this is wrong. So here we have a table scene and another the kitchen scene we saw earlier. And what you see here is what is really interesting. Here on the left lower image, you have this chair and this table with a really thin tabletop. And in this reconstruction here, you can see that we were able to reconstruct this table and even the chair, even though this chair is not that great visible in the color image because it basically nearly has the same color as the table behind it. We were still able to reconstruct it. And then we have more scenes where you have some loose furniture. Here you can see again really nicely the effect of the far plane. So we cut off everything which is further away than 4 meters. In this instance, for example, these stairs here are completely removed from the ground truth, and then of course from the prediction as well. So we only have this narrowed view, but usually this is enough. We could always navigate somewhere else to fill in this space. Of course, we could have generated one with more greater far plane. Problem is time. Generating this 1 terabyte of data takes 1 to 2 months, so it's not that easy to do this quickly. So finally, we only trained this whole thing so far on synthetic data. So I mentioned we generated all of this data and then we evaluated it on real scenes. So we tried to even do a sim to real transfer here. Because we have never trained on real data, we only trained on our photorealistic BlenderProc results and TSDF volumes. And now we have here as a color input, scene from Replica. Replica is a really small data set. It only has like 18 rooms, but they are all really high detailed. So someone scanned them in with a sensor, took probably ages. And then you get these nice images. And as you can see, even though we did not fine tune on real scenes, the transfer here is really well. You can see it figure out that this is a lamp here and reconstructed it, even though it predicted it to be a bit smaller than it actually is, probably because of the weird shading it had. Down here, you see a kind of artifact. So in our synthetic data set, SunCG, we assumed that all window surfaces are just filled with a milky glass, so you couldn't see through them. This probably threw off the approach here, where you can actually see inside of the cupboard, and then you don't predict this cupboard at all.
Were the scenes cherry-picked, or the examples here cherry-picked?
These are just random ones.
Random ones.
They're just random ones. There will be some
Impressive.
where you can actually see that it's not that great. For example, here, sorry. This video function in PowerPoint. So, for example, here you see how it reconstructed the bed and the background. Sometimes in these real scenes, the lighting is a bit different than in our synthetic scenes, and you can see how it then messes up with the wall reconstruction, as it's a bit tilted.
But this is still very impressive. Not cherry-picked, and it looks nice. Very impressive.
So here, these are one of the results which are a bit poorer, where you have here in the color image, a really thin object. So we have these chairs with these thin stripes of cloth, and they're so thin that you can actually see through them in the ground truth data, and predicting them then just fails. Same is for the table, which is mostly covered here by the chair, which is only visible to us humans because we can see through the chair, and this tiny bit here on the left side and this tiny bit here on the right. And based on that, it did not reconstruct this chair. Probably if we would have trained more on data which looks like this, would probably have worked better, but then this chair is completely neglected. And this is a risk of 3D reconstruction, because you usually don't want to neglect any objects of the scene. On the other hand, we have down here this bed scene where you can see that it got that there is free space behind this bed. So it had to understand, oh, what I'm looking at is a bed, without ever seeing a bed like this before, because we didn't train on this data set, or even this weird shaped light structure coming from above. And it had to figure out, here's a curtain in the back, which do not exist in SunCG either. And then it was able to reconstruct the space behind the bed. So now we talked a lot about having our color image and our synthetic normals. But in a real scenario, you don't have perfect normals for your scene. So what we did is we trained a unit to predict these normals based on color images on these SunCG images. Again, these were only trained on SunCG, not on Replica, which you will see later on generate some artifacts. So for SunCG, this works really well. So you can see the reconstruction is nearly the same. So the normals are really important. Without them, the performance drops drastically, but it's still quite well. Even though here, this chair was missed here, because the normals here around the chair were probably so messed up that it didn't think there is a certain object here. So you see there's still some pitfalls. It's not perfect, obviously. In Replica, we see it works quite well, though if you look at the normal images down here or here, you see some artifacts. Hopefully the zoom is not catching them. So there's some artifacts here in the normal image, just because the real world sensors do not completely behave like the sensors we use, the simulated sensors in BlenderProc. Same is true for here. And then you see that there's some divergence here in the top from the true one. Same down here. But it's still comparatively great for that we only have a color image of these replica scenes. In contrast to that scene where it completely failed. So here the normals completely neglected the bed and thought the bed is one plane. And then the approach thought, oh, there can't be a bed then, and it completely removed the bed, which is obviously not something you would want in a real application. So it works quite well, even though if we only have these generated normals. I think we could improve the results of the generated normals if we use stronger augmentations. Nonetheless, did we not have time for that in that particular work? But probably in the future, we're going to find a better approach to predict these normals, to make them more stable. If you can see down here or up here, it is weird stuff. And the network could still figure it out, even though it was only trained on perfect normals, which is quite reassuring though. So lastly, I want to show you what happens if you don't use our proposed loss shaping. So if you don't use loss shaping, then you end up with a scene which is much smoother. First of all, you see that we don't have any artifacts here, because the focus of the network is also on the hidden things behind the wall, but the details are lost. Here you see that it smooths over this couch, and in this scene, you can see that really well, how it removes all small details. It completely removed down here this table and the chair, which is not something you would want. So the loss shaping is crucial here to get the finer details, which would not be present else. Sometimes there are even weird artifacts which do not appear in the normal version. I'm not completely sure why this is happening. Replica, it's similar though. Here, even though you can see, wait, if you go a tiny bit back, we can see that this lamp here is completely missing in the prediction, which is present in the default version.
Ina is asking in the chat if is it possible to use normals in loss for TSDF as well?
Sorry, the last sentence in the
loss calculation, I think he said. In
the loss calculation, let me think about that. How could you use normals there too? So we provide them as an input. Well, of course, we could. What we could do is use a marching cubes algorithm on the TSDF volume, and then predict the normals and compare them to the predicted normals. That would be a way. But please think about, while training this, we only trained on the encodings, not on the complete TSDF volumes. We compressed them before training our tree net. So during, we could decompose them during training, but that would take so much time that the training would be so slow that it would take ages. So we had to train on the encoding, not on the completely formed TSDF volume. Okay.
The resolution of the normal images was the same as the regular image, or?
Yes.
Okay.
They're only smaller here that you can, because they're nicer to look at color images than normal images. They're usually quite plain for indoor scenes, as they usually only have a few colors for the surfaces present there.
Mm-hmm. William is asking, how was the training data distributed?
So we randomly sampled cameras in the indoor space of SunCG and used them as training data. Does this answer your question? There is no focus on certain rooms, just distribution of SunCG rooms that was present in the data set was used here. Does this answer the question? I'm not completely sure what you were aiming at.
Yeah, no, I was thinking about which parameters you were randomizing, but if the rooms were fixed, then you were just, I guess, randomizing the camera position. But
there is a lot of rooms in SunCG. I don't remember how many, but it's around 100,000 rooms. So there's enough rooms to generate enough camera scenarios. That's one of the great advantages of synthetic data. If you would want to generate that much real data, you would spend ages recording them. For this replica data set, which only consists of 8 rooms, they spend a lot of time generating these.
Now, I'm a big believer in synthetic data, and what I was trying to get to is like so one of the benefits of synthetic data that I see is the ability to tie the data that's generated to physical properties of the scene. So I was wondering if you were, basically generating rooms dynamically, but you're not. You're using
we haven't
ordered rooms, but lots of them.
Yes, SNDG is quite diverse. We didn't do that. There was one recent work at CVPR where they did that, where they didn't use SNDG because of the legal trouble SNDG is now in. As when we generated this was not the case, but now SNDG is kind of banned or not accessible anymore, should I say. And because of that, people are now just using ShapeNet objects and throw them in 3D boxes, which should represent rooms, and then they get their 3D scenes too. But as you see, this is not completely the same because the SNDG rooms were designed by architects. So there's a kind of similarity to human spaces where this would not be the case in such things. But for generalization purposes, of course, having this greater domain of randomization would probably help during training.
I don't want to delay you though. I want you to get onto your synthetic data generation pipeline bit because that's the bit I really want to listen to. So.
Good. So let me finish this one. We're nearly done. Let's finally talk about some quantitative results. So we evaluated this first on SNDG, which we trained on. There are some comparison methods up here. Problem is there is no one actually doing what we did. There's no one going from image data to 3D. The only approach which is close in that regard is Voxlets, where they constrain themselves to only tabletop scenes. So objects on the table, and they try to fill in the area behind the object, which is hidden by the object itself, which is close to what we do, but the scale is different. We tried this on full scenes, which are much more complex than just tabletop scenes, but this works already a few years old. At that time, of course, it was really groundbreaking. For this first work here, they are more focused. If you already have depth data, what can you do with that? And we didn't want to make that assumption because if you don't have a depth sensor and you use monad depth estimation, you already bring in all the errors monad depth estimation has. And there are a lot of them. They usually smoothen the output and they can be completely wrong, like our approach can be sometimes wrong if the objects are, for example, too small and such things. And if you already start from that, it's a lot harder to get better than that then. So we didn't try to do that. So we compared these two values here so that you can at least place these IOU values, these IOU and precision recall values a bit in contrast to our method. So we evaluated here with the default method I presented. Then we evaluated what happens if we increase and decrease the height of the tree. The performance is a bit different in these regards, but it's not really discuss worthy, I would say. Most important, what happens if you don't use our proposed loss shaping? What happens is that the IOU performance goes up, mostly because of the areas behind the wall. This is because it then doesn't have these weird artifacts we saw earlier in the video, and then the IU is better. This can be seen, especially in the SNDG scenes. But if you then compare the Hausdorff distance, which measures the distance between the two resulting meshes, you see that we are much closer with our loss shaping at the target mesh, which we are actually interested in. So you see here nearly double the performance or half the error when using our loss shaping. Here you see the difference between using the generated normals and the ones where we use our normal generation, our UNet I mentioned a bit earlier. Then we, of course, evaluated this whole thing on replica. And something noteworthy here is that on replica, you have a higher IOU value. And the main reason here is that replica has less super thin objects. In SNDG, it might happen that there's a room divider made out of wooden poles, which are quite thin, and predicting those is a mess. And sometimes it misses them, and then the IOU drops drastically. So there are a lot of these super thin objects in SNDG which are hard to predict, which are not so present in replica because someone actually had to scan in these rooms, and they probably decided these rooms should be clean so that we don't get any problems later on finishing up the data set. But you can see here the same thing, that the loss shaping helps in the Hausdorff distance measurement. Okay, so enough quantitative results. Let's summarize this whole thing. First, I showed an approach which can reconstruct based on one color image a complete scene, including hidden areas, so we can literally look around the corner. I showed that it is possible to use high resolution TSDF volumes if you compress them first. Before that, most people used was 128. There was Octonet, which used octrees to get to a high resolution, but complete pure TSDF volumes were never that high resolution before. And finally, we used gloss shaping in high dimensional outputs because it's so crucial, else the performance is not what you want. Finally, best part about all of this, it's completely open source. So you can scan this QR code or go to this website here and check out the code for all of the things I mentioned. The code is online. The generation of the TSDF volumes, the software we created for that, you could use this in any kind of scenario, even for objects if you want to. Then the software for the UNet or the training of our TreeNet architecture and so on are all online under this code. Yeah, here are some references to the few things I referenced. And do you have any final questions?
I have a question, but again, if somebody has before, go ahead. No, so I'll ask in the meantime. I was interested, Max, in the tree formation that you showed us. Maybe my question is because I'm not understanding fully, but did you think about connecting the different branches between themselves and transferring? Okay.
So what I thought, this should be probably, so if we have this connection here and this connection here, shouldn't they share the weights? That was what my initial thought was, because here we have a block of a certain space and here of a certain slice. And these two operations here should be kind of similar. So I used weight sharing between these two and these and this two and this one, but it didn't work at all. I tried several different weight sharing mechanisms to reduce the amount of parameters, but none of them trained well. Sadly, I really hope because that would reduce the amount of weights in the network.
Yeah, faster training for sure.
That much. I think the training time was even bigger because it has to share the weights, which makes it a bit more problematic.
On the back propagation, yeah.
Yes.
And I actually wanted to ask about concatenating the results. So if you have the two branches, going to the sides, then taking from branch right and adding the results to branch left, and then
in between the tree, you mean?
Yeah, in between the trees, in between the branches.
But keep in mind that we do this tree splitting to get down to these single small depth slices. So if we put that information in from another depth slice, we would break up the structure a bit. It might help, but I'm not completely sure how much. It might be, for example, helpful to connect these two down here because they are neighboring. Maybe there is some shared information here which could be used. But I assume that if we put them back here in this 3D block and then we can use 3D convolutions of view at the end to make sure that information is then finally shared across the 3D volume.
So that's exactly the point that you mentioned. That's the thing, breaking the structure. What's the intuition to understand that the structure could be broken if you connect different branches? Because on the end, you're trying to predict a specific slice, yeah? So during training, the weights will align accordingly so that the prediction will be closer, right? So how does... So
let's pick one of these. I just noticed that these two images are flipped. So it's not super easy to understand, but this blue node here on the right corresponds to the super left node here on the left. And this depth slice, all information which is in this depth slice should be represented in this blue node. And this one here is this purple node, right? So now you could, of course, mix them before you put them back into a 3D volume. We haven't tried it. I believe, though, that it wouldn't work that well. I believe it's better if you split them first and then put them back all together so that you can use all the information of your 3D volume at once. Because if you could try that. I haven't tried merging the last two here before merging them back to a block, probably because I feared it would be, again, an additional overhead. This is not a super simple architecture to train. As you heard, the data for this is a terabyte big in a compressed form. So training it was a hassle and the training times weren't that short either. It's not that you could train this in a few minutes. And we couldn't use a pre-trained network because there was no structure like this before, as far as at least I know.
And this leads me to the next question, which was exactly how did you do training? So I think you mentioned a month of training. Do I remember correctly?
No, a month of data generation.
Yeah, right.
Training would be, yeah. Sadly, I don't work for Facebook, where I need a cluster for a month. People leave. So in this instance, especially in the beginning, without this, the training took like 2 weeks till it converged, maybe 3, depending on how the learning rate and parameters were set up. But with this, we could bring it down to a few days. Now it can train in 4 to 5 days, depending, of course, on your GPU.
What GPU did you use?
Yeah.
This was trained on a 2080 Ti.
Okay. Not something I can, from the top of my head, remember what it is.
So it is a consumer graphics card.
Okay.
It's not a specific, it doesn't have that much memory, which even reduces the batch size and stuff like that, because if I remember correctly, we trained with a batch size of 2. So we didn't use any batch normalization.
Oh my goodness.
Yes.
Oh my goodness. Okay.
A bit of unstable learning rate. Gradient is something normal in such regard, because what we try to reconstruct, even this compressed volume is still big. It's still big. 32 to the power of 3 times 64 is still a big output. Still big. And we perform a lot of operations to get from a color image to a 3D space. It's not just a simple problem, sadly, or luckily.
By the way, maybe it's a good time to mention to the audience, 512 in the power of 3 resolution, the end resolution that comes out after decoding, right? This is quite high. Usually when I see research in 3D reconstruction, the resolution is much lower because of computational time problems. Yes. So that's one of the interesting things in this research in my eyes.
I spent so much time on this research. So in the beginning, I had this one idea. I wanted to go from 2D to 3D with only 1 color images. And along the way, I had to invent new things to make it work, because it just didn't work. So I added this and this and this. It was not just one leap. It was all the combination of the little things I showed today, like the tree net architecture, or the loss shaping, and the loss shaping in the tree, which actually made it work in the end, or the compression, so that we could get to these high resolutions.
Mm-hmm. Yeah, for sure. A lot of, when you mentioned the data generation part with the color for each point normalization, I think you said TSDF volume encoding. Each part here is not trivial. This was just this one, yeah. Yes. So this slide. So each part in the second row is a work by itself. We just passed it briefly, but this is a work by itself. Tough stuff.
Yes.
Nice.
One thing which I would have really loved to do would make that data set public. Even though it's a terabyte big, that would have worked somehow. The problem is the data set, which is based on SunCG. For the people who don't know, Facebook and Princeton have published SunCG in the past, and then they got in legal troubles because a website, if I recall correctly, I don't recall the name of the website anymore, which is an architecture website, claimed that Facebook and Princeton and the organizers behind this crawled their website and offered the data of these website as a public data set. And then they got a legal argument, and since then SunCG is not publicly available anymore. For that reason, I cannot make this data set public, because it is based on SunCG. Luckily, a few weeks ago, months I should say now, Alibaba introduced a new data set for indoor spaces, which is called 3D Front, which could be used to generate a new data set, because it's currently available. Problem is it's still missing doors and windows for some reason. I cannot phantom, and maybe they will add them in the future, and then I can regenerate some data for you. For now, everyone can just generate their own data if they have enough computational resources and disk storage.
Yeah.
There were some questions which I have not answered yet. First, regarding SunCG. Maybe try Googling it. Maybe you find a link a few months ago, like in July, there was a link somewhere that you downloaded it, sadly down. Yes.
Yeah, I don't find it on dataset search. I don't find any torrent for it, anything else. The best I have is someone saying, send us an email and maybe we'll give it to you. Maybe not. So
Nice.
Sounds fishy.
Yeah. the illegal places where we computer scientists trade data sets. I'm a bit disappointed that it came to that point, but yes.
I see Manuel here sent a reference to a paper, multi-layer depth. Manuel, if you're still here and you can share like a bit the idea here in this paper and how you think it relates well. It'll be interesting to hear.
So what I got from the paper is like, basically, if you know the concept of depth peeling from computer graphics, basically they represent the scene as multiple images. So it's similar to depth maps, but not quite similar or the same. But at least it's like basically image-based. Like you have basically multiple images of the scene which store different depth values.
So it is a bit similar to the multi-view approach or approach which I mentioned under the different 3D reconstructions you could choose. So
the input is actually the input is actually like a single RGB image.
Mm-hmm. But you try to predict fixed other camera positions.
It's the same camera position, but like the things you try to predict are like just different depth values, as far as I understood.
I see. So as I said, there are a lot of different ways of how to represent 3D data well. We picked TSDF because I feel like the link between color pixels and 3D information is really crucial, especially if you're more complex than just singular shapes.